Hello everyone! Welcome to the lecture video on deflection angle traverse of the ABE48 laboratory. In this lecture video, you will be oriented with a proper execution and how we establish a traverse based on deflection angles. Before we go on with the procedure, let us have first some definitions of important terms that you should know as we go along with the discussion. Our first term is the traverse, and if you still haven't discussed it yet in the lecture, traverse is defined as a form of control survey which consists of a series of established stations tied together by angle and distance. Traverses are used for the establishment of horizontal control points whose positions have been previously determined. The key terms here are angle and distance. For us to call it a traverse, the angle and distance between two adjacent stations should be known, because that's how we define the location of traverse points in a horizontal plane. Now, there are two general types of traverse. The first one is the open type traverse, and it is something that originates at a point of known position and terminates to a point of unknown position. The establishment of the open type traverse is a preliminary activity for route surveys or for the construction of linear facilities such as highways, pipelines, canals, etc. Well, as you can see, the stationing in this example is something that is similar to your profile leveling exercise. And if you still remember the things that you did in that exercise, only the horizontal distances between stations were measured. But in field practice, angles should also be included. So let us say that the first station is our starting point. We occupy this station using our instrument, orient it to our reference meridian, and determine the angle between the meridian and the next station. In running this type of traverse, we occupy the stations in a successive manner. We occupy then the station 1 plus 0, 0, prolong the previous line using our instrument, and determine the angle between the extended line and the succeeding line. You repeat the process all over again until you get to your termination point. Only at this point that you can determine its location. The open type traverse may extend for long distances without the opportunity for checking the accuracy of the ongoing work. But normally, the GPS tracker is being used to verify the location of points. The second type traverse is a closed traverse, and unlike the open traverse, the closed traverse forms a closed loop by starting from a point of known position and terminating to that very same point. One of the many ways of running a closed traverse is similar to our previous example from the open traverse. Occupy the stations in a successive manner while determining the angles and distance in between stations. But this time, you end up to the point where you started. This type of angle that we are making here are actually the deflection angles. And this method is what we will be employing in this exercise to establish a closed traverse. So basically, we will be showing you virtually how to prolong previous lines and measure deflection angles with repetition using the theodolite. We start the procedure by establishing our stations in the ground. So we have a simple polygon with 4 sides and whose stations are labeled as station A, B, C, and D. We start by occupying station A with our theodolite. It is also important that you pay attention in the LCD shown on the top right of the slide, as the horizontal angle readings of the simulation will be displayed in here. We try to look at the setup in top view so we can see the horizontal angles clearly. Indicated on top is the format of your table for this exercise. The copy of the table is also indicated in the exercise guide to be provided to you by your laboratory instructor. Before you do any angle readings, make sure that the theodolite is perfectly leveled and centered over station A. Afterwards, determine the bearing of the first line, which is line AB, by referencing your theodolite towards the magnetic north using an external compass and by pressing the zero set button twice. In this manner, you will notice that the horizontal angle reading in the LCD will be reset and will indicate 0 degrees. Aim for the station B using the telescope. Your field of sight should be in such a way that the vertical hair of the telescope is bisecting the hub or the pin. This can be achieved by finely adjusting the horizontal clamp screw. The angle reading in the LCD is the bearing of your line AB and is being read as 8 degrees, 11 minutes, and 21 seconds east of north. It is important that you already know the designations of the directional angles at this point of the lecture video. Never mind the vertical angle reading, as they are not our concern at this exercise. You record the bearing at the bottom of your table because that will be necessary later on when you orient your traverse during the map preparation. After determining the bearing, we are now ready to determine the deflection angles. Afterwards, press the hold button twice to lock your reading. This way, your angle reading will never change no matter how much you turn your theodolite along the horizontal axis. Have a backsight in the previous station, which is station D. It is actually your choice on how you designate your stations. But for this example, since we are occupying station A, my previous station is the station D, and my next station is station B, because the stations will be successively occupied in a clockwise direction. Okay, so moving on with the lecture, press the 0 set button twice and have your angle reading set to 0 degrees. Afterwards, place your telescope in reverse position. By doing this, we are turning our line of sight by perfectly 180 degrees from station D. In this way, we are already extending the line of AD from A up to how far your line of sight can get. This is what we actually mean when we say that the theodolite can prolong the lines by having a backsight on a point and plunging the telescope in reverse. So going back into the procedure, release the hold on your angle reading by pressing again the hold button twice. In this way, you can now read horizontal angles freely. With the extended line as your baseline, read the deflection angle of line AB by having a foresight on station B. The angle reading that register in the LCD is the deflection angle of line AB. Have it recorded in your table. Under the telescope position column, indicate reversed, since we did the reading while the telescope is in reverse position. And record the value of the deflection angle as well. But the reading doesn't end here. We read the deflection angle twice to eliminate the collimation error along the horizontal axis. Press the hold button twice again to freeze the angle reading and have a backsight on the previous station while your telescope is still in reverse position. Next up, normalize the position of your telescope to extend once again the line of AD and release the hold on your reading by pressing the hold button twice. Aim for the next station using your telescope. In your table, have your deflection angle recorded and the telescope position, which is normal. But since we have read the deflection angle of a single quantity with repetition, we normally see an accumulated angle or value being displayed in the LCD. To compute for the MPV, simply divide the accumulated value with the number of repetitions and have the computed value recorded under the MPV deflection angle column. together with the direction of your turn. In this case, we have the angle to the right, so indicate letter R after the angle. The length of the side AB will be measured using tape, starting from point A to point B and from point B to point A. That is why you are seeing two values of lengths here, but only get the average of the two values to get the MPV of the length. Okay, so afterwards, we progress along the traverse by occupying the next station. Once we have leveled our instrument and have it centered over station B, we just have to repeat the same things that we did when we were on station A and press the zero set button twice to reset the angle reading. Plunge the telescope in reverse and aim for the next station. Have the first angle reading recorded in your table, in line with the reverse position of the telescope. After that, press the hold button twice to freeze your angle reading and have a good aim of the previous station once again. Normalize the position of your telescope. Release the hold on your reading. And have a foresight onto the next station. Have your data recorded in your table. And compute for the MPV of the deflection angle by dividing the final angle reading with the number of repetitions. Have it recorded in your table as well as your data for the horizontal distance of line BC. You repeat the same procedure until you get done in all of the stations of your traverse. Now, you can check for the accuracy of your traverse by simply adding up all the values of the deflection angles and see if the sum is equal to 360 degrees. So why 360 degrees? Imagine if we slowly take the traverse out of the picture while just retaining the angles. Let's see what will happen. Well, the circle in this illustration may not be perfect, but theoretically, the sum of all the deflection angles should be equal to 360 degrees. If it's not 360, then the traverse is not mathematically closed, and you have to do the traverse adjustments. But that topic will be discussed in a separate lecture video. Our previous example only showcased deflection angles to the right, but if we happen to encounter a traverse with a deflection angle to the left, just simply treat it as a negative value. So when you do the summation of all the deflection angles, then it should still be 360 degrees. In your field notebooks, we will be expecting to see these things: the table of measurements, similar to our example, the sketch of your traverse that is oriented to the north with proper labels and showcasing the measurements you have done, sample computations, and conclusion since we do not have guide questions for this exercise. The materials essential for this exercise are theodolite, tripod, field tape, mallet, and hubs or chaining pins. And that's all, folks. The video lecture ends here. If you have questions, just leave us a message. Thanks for your time, and we hope you well.